Can you see my screen?
Yes.
Okay, great. And well, thanks again, Vipin, for the super interesting keynote. I'm Johannes Gerke from Microsoft, and it's my pleasure to welcome you to the ICDE 2020 award session. We'll dive right away in and go to the first award, which is the 2020 IEEE Innovation in Societal Infrastructure Award. Introduce this award, I have the pleasure of giving this virtual stage to Professor at the University of Maryland, College Park, and IEEE Computer Society President, Professor Lila De Floriana.
Thank you very much, Johannes. Good morning to everybody, to all attendees. It is a great pleasure to be here. In these actually very challenging times, I think it's very important to take all opportunity to come together and to recognize the accomplishment and contribution of our colleagues. And this is for several reasons. First of all, we want to celebrate them, those that are receiving the awards, and to celebrate their achievement. But this also actually will inspire the rest of us when we hear about their efforts and success. Last but not least, I think that by celebrating the prestige of our profession, I think we can demonstrate how scientists, engineers, and technologists contribute to our global community and how much they have done to lead to this technologically advanced world. My big thanks to the organizer and the other participants for their creativity and flexibility in addressing all the challenges of putting together this ceremony. Thank you very, very much. It is actually my great honor to be here to participate in this celebration today, representing the IEEE Board of Directors to present the 2020 IEEE Innovation in Societal Infrastructure Award. This award is sponsored by Hitachi Limited and by the IEEE Computer Society, and recognizes significant technological achievement and contribution to the establishment, development, and proliferation of innovative societal infrastructure systems through the application of information technology, with an emphasis on distributed computing systems. This year, we are honoring IEEE Fellow Masaru Kitsuregawa for contribution to big data collection and analytics of real-world problems with advanced data engineering technology. Professor Kitsuregawa is Director General of the National Institute of Informatics and a professor with the Institute of Industrial Science at the University of Tokyo in Japan. He is a leader in fostering worldwide research collaboration with the societal infrastructure system that connect the global data resources to address real-world application. Professor Kitsuregawa has led the development and deployment of big data platform on environment and healthcare. Since the early 80s, he has accumulated Earth environmental data from many real-time sensors. In 2019, his data integration and analysis of their system grew to 35 petabytes and is now used by scientists and government agencies around the world for applications such as weather modeling, disaster management. DS provides satellite imagery, radar, and river water gauge data for real-time flood prediction and proactive dam discharging. He is now working on building the Sphinx big data platform with 200 billion medical claims record from Japan. Sphinx enables new discovery on nationwide statistics for drug usage and time series analysis after operation. These discoveries are being used to improve medical treatments and healthcare system efficiency. So, on behalf of the IEEE Board of Directors, it is my great pleasure to congratulate the IEEE Fellow Masaru Kitsuregawa, the recipient of the 2020 IEEE Innovation in Societal Infrastructure Award. Congratulations. Because we are presenting this award virtually, Professor Kitsuregawa has asked me to read the following acceptance remarks on his behalf. Hello, everyone. I'm very happy to be honored with the IEEE Innovation in Societal Infrastructure Award. This IEEE award is usually given in an IEEE level ceremony, but I chose to receive it here at ICDE among many old friends. I had quite a few ICDE papers and served in every position of ICDE organization with fond memory over more than 30 years, and in my term as the steering committee chair just a couple of years ago. In addition to publishing paper in the 80s and 90s, I work more and more in building data platform for application that I have direct benefit to the society. DIA stands for Data Integration Analysis System, and we have been building it for Earth Environmental Information System for more than 30 years. DIAS is being used by scientific and government decision-making application, Japan, Sri Lanka, Myanmar, Thailand, and African countries. Concrete examples of deployed application include flood mitigation in several locations, malaria spread prevention in South Africa, and drought management in Brazil. We are also working on new application and data set as I give this talk in an online conference due to the coronavirus pandemic. We are collecting Twitter data and building real-time analysis system. A Japanese medical doctor who worked in New York City until recently told me that the most effective information source has been Twitter since it is really real time. Again, thank you very much for such a prestigious award. Please stay safe and stay healthy. So this concludes this acceptance speech, and I want again that you join me, please join me in congratulating Professor Masara Tsuguregawa for his impressive achievement. Thank you.
Let's give Masaru a hand.
Thank you so much.
Great, thank you. Do everybody still sees the slides? Okay, I assume so. So let me.
Yes, we do.
Okay, great. Thank you. Then let me move on. Our next section in the award session here is about the 2020 IEEE Technical Committee on Data Engineering Awards. I had the privilege of chairing the awards committee this year with an excellent team consisting of Natasha, Paolo, Mike, Luna, and Sunita. And it's my real pleasure to give out or to announce the 2020 IEEE Technical Committee on Data Engineering Rising Star Award, which goes to Alvin Chung, who is now at UC Berkeley, for contributions at the intersection of data management and programming languages. And with this, I'm giving the virtual stage to Alvin for his award talk. Alvin, can you please take over?
Great, thank you. Let me try to share my screen. Does that look okay?
Yes, looks great.
Great. So good morning, everyone, and thank you so much for the introduction, Johannes. I'm extremely humbled to be the Rising Star Award recipient this year and would like to thank the awards committee tremendously for giving me this great honor. So in the next few minutes, I would just like to do a short recap of our current work on optimizing database applications, which hopefully might inspire some new ideas for the audience. So from social networking websites to mobile games to banking, booking plane tickets, managing health records, and accounting software, we pretty much interact with applications that store data on persistent storage on a daily basis. So in general, these applications are usually written in a general purpose language and is hosted on an application server, while the database is hosted on a separate database server. So when service request comes in, so let's say someone goes to a website, the application will contact the database in order to fulfill the request. So our group has been working on optimizing the backend of these applications, both in terms of identifying problematic spots for performance and also helping developers build them easily. So the whole story starts with one of our projects called Hyperloop, which was intended to build up different tools to identify performance shortcomings in database applications in the setting that I was mentioning earlier. So after a couple of papers, one of the more surprising things that we found was the fact that among many of these open source database applications, and I included a partial list here on the right, turns out that many of them still have a lot of performance issues. And by the way, these are not like, toy examples or like, student projects. We're really talking about some of these well-known applications that you and I might be using on a daily basis. For example, OpenStreetMap, GitLab, that kind of application. So we found all these different performance issues, and perhaps even more surprisingly is the fact that we can still get quite a bit of speed up by just doing a little bit of code tweaking. So that got us interested into looking into like what is actually going on across all these different database applications using the setting that I was describing earlier. We dived into these applications, and turns out that there are a bunch of things that these applications tends to do. For example, we took a look at one of these applications, and then they turned out to use a log LSM tree as opposed to a B+ tree to optimize their performance. So that's what we discovered after we told them that we found a bunch of performance bottlenecks in your application. So this basically means that they are just customizing data structures in order to achieve performance improvement, which is great. Another application set of developers that we talked to ended up running the aggregate queries, not in the database, but on the GPUs to get their performance improvements, which is also awesome. And that basically teaches us a lesson that customizing execution platform is another way to achieve performance gain. And yet another app turns out to use a customized hybrid optimistic concurrency control along with snapshot isolation to run their queries for transactions. And again, this is just like another story where customizing a transaction protocol can also give you performance gain. Now, needless to say, I mean, all these basically there's a common theme across all of them, right? Which is the idea of specialization. So it comes without saying. Well, again, we learned that like all the way back from Mike Stonebreaker that like one size doesn't fit all. But perhaps a little bit of a joke here, right, is basically talking about like why are there so many specializations? And for all these different specializations, people have to manually identify the bottlenecks and then implement them completely manually. So that basically got us to think about like what would happen if we start building different ways to try to automatically generate these specialization targeted for different applications. Or in other words, we just try to robotize Mike Stonebreaker in a sense. So at this point, you might say, well, that's easy, right? And why don't we just build a machine learning model and then that can do everything, right? Well, it turns out that that doesn't necessarily fit the entire bill. So for instance, here are some of the things that we want to achieve with this auto-specialization work. For example, we want to be able to generate code that is explainable. We want to be able to generate code that is debuggable by humans, not by machine learning models. And furthermore, we want to generate code that is actually correct. We don't want to break the original developers' semantics of the applications that they are trying to implement. So there are a couple of things that we ended up being able to utilize in this regard. For example, one thing that we did was we started looking into code analysis. After all, we do have the applications that are available to us. I mean, so why not actually take a look at what people are trying to implement and then use that as a way to drive the optimization or specialization. Another thing is also recently, there has been a lot of advances in formal methods and also across different fields in computational logic. So why not leverage those advances as well in trying to do automatically specialize applications. So we ended up doing a little bit of exploration, and we came up with a bit of a paradigm in terms of generating these specializations for different applications. So we'll start off with a specification of what we're actually trying to achieve, and I'll give you an example in just a second. And then we'll just describe what we're looking for in the search as a search space. I mean, what are the possible solutions to the problem that we're trying to solve given the specification? We would then try to craft different types of search algorithms. And of course, there we can definitely use machine learning for that purpose. And for any of the candidates or any of the ideas that the search algorithm returns, we'll then try to verify them formally in order to prove that they are actually correct with regard to the original problem statement that we have in our hands. And if all goes well, we then have the specialized implementation that we're looking for. So before diving into details about telling you how we instantiate this particular paradigm of doing automatic specialization, let me just spend a few minutes to talk about how do we actually go about doing verification in this land. So for that purpose, we built solver called Cosette, which is able to reason about SQL and also other kinds of relational queries. And the reason why it's called Cosette, as someone was asking me earlier, was not because it has the connections with the play, but rather because we basically built this on top of the Coq-proof assistant and the Rosette SMT solver. Now, the key idea behind Cosette is the fact that we basically have a functional encoding of queries as opposed to modeling queries as something that return a list of results. For example, we remodel a relation as a function where given a tuple simply returns a number, where 0, for example, simply means that the tuple isn't in the relation itself. And a predicate in this world is just modeled as a binary number, 1 or 0, the kind of numbers that we all understand. This actually wasn't our innovation per se, but actually came from an innovative and forward-looking paper back in 2007 on provenance semi-rings. The advantage of encoding queries this way is now we no longer need to reason about lists or backs, but we just need to reason about algebraic formulas. For example, let's say we want to prove in this case that these two queries here are equivalent, and I hope you can see that they are. So in this case, we are simply pushing union into the base relations as opposed to doing it after the selection. So in this case, we can simply encode them using algebraic formulas. So the base relations now becomes two simple functions that return a single number, r of t and s of t, where t here is a tuple, and they get multiplied by the predicate p here. If the tuple t passes the predicate, then the predicate function will return 1, meaning that we just return the original multiplicity of the tuple t in both r and s. The details are not important here, but what I want to show you here is the fact that by encoding this algebraically, deciding whether two queries are equivalent or not can sometimes reduce to just reasoning about mathematical properties. For example, in this case, that multiplication actually distributes over addition. And this kind of reasoning can be easily encoded using various kinds of proof assistants and SMT solvers and other kinds of solvers that the formal methods friends in the computer science community has recently been producing. We have been using this kind of encoding for queries and to build this solver, and I invite you to actually check it out if you're interested, where we have this interface where you can just put in different queries and it will just tell you whether we can find a counterexample or not. Now, armed with this kind of verifier, we then go on to apply our paradigm that I showed you a couple of slides ago to try to do automatic specialization. One of the things that we built is a data structure synthesizer. So let's say we want to build an application that looks like Slack that I'm showing you here on the left-hand side. Slack, in this case, has something known as channels. It has things like users. It has things like messages. So the question now becomes like, how do we actually want to store all this data in the database? If we took a database class, which I assume all of us have, one thing you might imagine is to basically do BCNF kind of normalization. We can store each of these kinds of data, right, into separate tables. We would have a channels table, a users table, and a message table, and then we'll have a separate mapping table that maps across these three different things. That's all good and well. However, that might not be actually fitting in terms of what the application is trying to do for querying purposes. So for example, we might be better off if we're able to store things in a nested manner. So in this case here, I'm showing you an example where we have embedded the authors of the individual messages into the actual message object itself. So notice that we're no longer sticking in relational land anymore because we have this nested data model. And it actually goes on, right? So we can actually do all the way nested up until just embedding everything inside a channel. So all these are actually valid designs in terms of storing how to store persistent data, and they all have to do with the fact that how the application is going to issue queries and what kind of queries is the application is going to issue. So we can now try to specialize a data structure only targeted for this specific application, right? For instance, in this case, Slack. However, we have another slight problem here. So given these kind of new funky layout, right? Because the data is no longer sitting in a relational or or flat, unnested way, we now have an issue in terms of how we're going to execute these queries. If things were in relations, this is easy because it's just basically executing an SQL query. But since we have this kind of funky layout now, then it's no longer clear how to actually do this. Well, we can also basically treat this problem as another search, right? Where we're basically trying to find a possible execution plan given the layout that we have, right? So that's where we basically instantiate our paradigm that I was talking to you earlier. In this case, the search space is exactly the grammar of data structures and query plans that we can execute. And by query plans, I'm really talking about this kind of low-level code here I'm showing you here on the right-hand side. And for specification, we basically have the original SQL query that the user wrote as part of the application, along with just the simple design of storing everything in the BCNF form in the relation. We craft our own search algorithm in terms of using enumeration and integer linear programming. We use Cosette for verification purposes. And then at the end of the day, we'll be able to come up with a bunch of different data structures and query plans that are tailor-made for the specific application that we're trying to deal with. So this is all good and well, but now let's also try to address another problem in terms of figuring out where to actually execute all these query operations. As I said, people realize that utilizing different kinds of hardware, different kinds of framework is a good idea. So that's yet another kind of specialization that the application might want to do. A concrete example might be the following. So let's say we have vanilla Java program, right? And then we want to allow the Java program to basically leverage something like Spark, which is executing things across a number of data nodes, right? So you might think that's easy. I mean, we just need to rewrite part of the Java program to use the Spark API. And if for the developers out there, you might even think like we can automate the process by just building a compiler. Well, unfortunately, that's not just the end of the story because of the fact that we might have other platforms that we want to execute this piece of Java code as well. For example, we might want to execute in a traditional database system. We might want to execute on a machine learning framework. We might have other pieces of source code that we want to translate and so on and so forth, right? So the problem kind of goes out of hand pretty quickly, not to mention the fact that Spark internally might also be executing across different platforms as well. So when I first showed this slide, people would laugh at me when I was showing something like Fortran or COBOL, but perhaps it's no longer a joke, right? When we're actually looking at people trying to do this more recently because of the pandemic. So for this particular problem, we started building something called verified lifting, which is an idea that allows us to build these compilers kind of automatically in order to achieve specialization. So let's say I want to translate this piece of code here I'm showing you on the lower left, which is a vanilla piece of code written in Java, and I want to be able to translate that into Spark or MapReduce in this case. Now, instead of building a compiler directly, imagine we first try to rewrite this program into a high-level intermediate representation, in this case, a kind of MapReduce thing, but where programs are written using mappers and reducers. I claim that if we have this program in this IR, then doing code generation into actual executable code is pretty easy. Well, the question becomes, how do we actually get the program into this high-level representation to begin with? We call that process lifting, and that is yet again another instantiation of the paradigm that I was talking to you earlier, where in this case, the search space consists of programs that we can express using the high-level intermediate representation that we invented. And the specification here is just the input program that we have. So the one here on the left-hand side here I was showing you earlier. For search algorithm, in this case, we use something called inductive program synthesis that we created. And for verification, we just use off-the-shelf tools like Z3 and also Cosette that we came up with. And by turning the crank, we're able to come up with application-specific execution plan, just like the one that I'm showing you here that utilizes Spark. We've actually applied this methodology in particular to a bunch of different applications, including web applications, allowing them to use database systems to get tremendous amount of speed up. We applied that to other kind of data analytics applications to allow them to use Spark, and also outside of database arena, we have also used this same methodology to allow image processing operations to use GPUs and also programmable switches. Going forward, however, we would like to apply the paradigm that I was telling you earlier in terms of trying to specialize other things. For example, transaction protocols, how data should be distributed across a set of nodes, and even trying to create hardware accelerators that are specific to the application in mind. So these are some of the areas that we are currently exploring, and I would love to talk to people in the audience who will be interested in looking into that as well. So in sum, I'm really grateful to be the recipient of the award this year, and I specifically like to thank my advisors, Professor Madden and Professor Solar Lasama, who gave me a lot of guidance and help, and also all my mentors over the years. And of course, all the junior researchers who I get to work with over this number of past years. And of course, as the usual saying goes, all the mistakes are mine, and all the great ideas basically came from them. I would also like to thank the industrial sponsors and also my colleagues at the various academic institutions that I've been able to work with over the past years. So in this short talk, I basically gave you a brief overview of some of our current work and also some of the things that we're currently looking into in terms of specialization. I've told you about Hyperloop, a platform that we built to detect performance problems in database applications, a query equivalence checker called Cosette, and then 2 specific instances of where we have applied the automatic specialization paradigm in trying to specialize different aspects of database applications. With that, thank you very much, and I'm happy to take questions.
Thank you, Alvin. Are there any questions? Right now, I didn't see any open questions in the chat. Maybe I can let me ask one question myself. So it's really amazing, and especially given that this is the award is for the body of work in the first 5 years after the PhD, and so it's really amazing to see all of what you have done. So what do you see sort of as next steps here? I mean, these are sort of all, I feel like, different parts of sort of a bigger problem that you're chopping away at. What do you see as sort of the bigger vision in the next 5 to 10 years here?
Well, I would like to think one of the potential ways to move this forward is to see how we can build other kinds of techniques to try to specialize for different aspects of database applications. I mean, after all, we just basically try to scratch the surface for the past few years in terms of specializing different specific aspects. I think one cool idea would be to try to bring all of this up together into building some a new system, right? Or maybe a new engine per se, right, that would generate these different database systems. So that's basically one of the things that we're looking into currently.
Okay, great. Well, thank you very much again, Alvin.
Thank you.
I would like to point out to everyone, let me actually see whether I can take over again. Okay, before we go to the 2020 10-Year Influential Paper Award, I'd like to say that we actually have 4 TCDE awards. The Early Career Award is only one of them. And we also have the TCDE Impact Award, the TCDE Education Award, and the TCDE Service Award. We didn't receive any nominations for the awards this year. So please, for next year, nominate your colleagues. These are highly prestigious awards, and it'll be great. And we have so many deserving people in the community, and I really hope that we can give them out next year. With this, I'll conclude the session now with the IEEE ICDE 2020 10-Year Influential Paper Award. And introduce this award, I have the pleasure of giving the stage to the founding dean of the Graduate School of Data Science at Seoul National University, Professor Sang Cha. Sang, do you want to take over?
Hi, Johannes. Thank you very much. This is Sang Cha from Seoul National University. Actually, I'm in the same time zone as Masaru, but yeah. I'm the chair of ICDE 10-Year Influential Paper, and this award is given by the steering committee of ICDE. And I'm pleased to announce this year's award is given to the authors of the paper, Hive, a petabyte scale data warehouse using Hadoop. There are 9 authors, and let me introduce one of the authors, Joydeep Sensama. Joydeep?
Yeah. Hello. Hi. Hey, this is Joydeep. Yes.
Can you turn on your video?
Yeah, absolutely. Yeah. So give me a sec. Let me share my screen. Okay. Thank you, Professor Shah. So I have, so first of all, thank you very much to the team, to the committee to recognize the Hive paper. It's been a while. It's brought back a lot of memories for us. So I'll just give you a quick retrospective on the work we did, and to some extent on the work that we're doing right now. So I'm here representing the early Hive team. Second, let me see if I can just. So I have the names of all the authors and what they are doing today up on the screen. A few of us are at a startup called Qubol. Ashish, myself, and Namit, we are at Qubol, where we provide a big data analytics service in the cloud. So we are still grappling with big data and stuff like that on a day-to-day basis. A few of our colleagues are still out there doing the same. So Zheng Chao is at Uber. He heads the data team at Uber. Raghutam Murthy has an interesting product. He has a company called Data Coral, which is building sort of materialized views kind of stuff. Prasad is at a healthcare startup, also doing data stuff. And so is Suresh. He's at an e-commerce startup. So you see all the authors. We have a lot of more gray hair after 10 years, but a lot of us are still doing engineering and building things. Thanks to this award, actually, we had a 10-year get together. So thank you again for the organizers for, having giving us a bit of impetus to sort of, reconnect and talk about what we are doing at this stage in our lives. So let me go back a little bit and discuss, on the work we did, and I'll try to sort of just do a little bit of retrospective, as well as, what the practitioners in the field are still sort of working on and what we see on the field. So first of all, Hive was obviously, not just the work of the authors of this paper, but a much larger effort with significant community beyond that. I spent some time at Yahoo, and there were other. Raghutam was also from Yahoo, and we were heavily inspired by some of the systems that were built at Yahoo, which were never open sourced and not as well documented publicly or even presented in conferences. But there was a very large scale petabyte-sized data warehouse called Mina built on flat files, and a lot of inspiration for the work we did in building Hive. Some of the architectural patterns came from there. And of course, we relied on Hadoop, which was built by Doug Cutting and the team at Yahoo. We had an outstanding team at Facebook. One of the the lucky aspects of working at one of the best funded, most sought after startups is you get to work with really great colleagues. Aside from the team in the paper author list, we had folks like Dhruva, Hairong, Yong Chang, and a whole bunch of folks who really sort of helped us achieve this output. And most of us moved on from Hive around 2011 or 12 timeframe, and the fact that the project is as popular as it is today and continues to be used widely is because of the community that took over. There was a very large team at what the companies that used to be called HerodWorks, now called Cloudera. I don't have all the names, but some of the folks that built on our initial work were Alan Gates, Owen O'Malley, Arun Murthy, Ashutosh Chauhan, and there were many others that I could not list on here. So just again, a retrospective, some distant memories. So we started almost the whole team here, on the author list. We started working at Facebook around 2007 or 2008 timeframe. We were the data infrastructure team, and basically what we were asked to do was to collect, process, and analyze the data that was being generated in the organization, and to make that data available for analysis throughout the organization. When I joined the company in 2007, there was an Oracle database, and there were 2-3 people essentially babysitting that database to make sure that it did not crash while data was being loaded into it. And somehow, things were sort of creaking along. So there was an urgent need to, do something that was more scalable. And Facebook at that time was growing amazingly fast. It's like, I think we look at a lot of exponential charts today because of the coronavirus situation, and that time Facebook was growing exactly in a similar manner. We decided to use Hadoop in around 2007, so we said, okay, let's we need a scalable storage. Let's start using Hadoop and MapReduce. Tried building, loaded a bunch of data, tried building some toy applications. And then we quickly realized that we could not really achieve our goal of democratizing access to this data and like essentially get out of the job of writing sort of custom reports and applications using MapReduce unless we built a system that was more accessible to a lot more people in the company. So we started building Hive as a side project, really. All of us had a day job, which was actually to, frankly, more as data engineers. We were helping like sort of run these data pipelines, collect the data, sort of build some initial data pipelines for different products that the company needed. But as a side project, we started building a SQL engine on top of Hadoop. And we really had 3 goals in mind. One was we wanted to reduce the amount of chaos in terms of schema management. And so we built a catalog that would store all the schemas. We thought that SQL was the natural interface, an easy interface that would make it very easy for the rest of the organization to analyze this data. But we also saw that in our environment, the engineers were also analysts, and they used to love programming in scripting languages, particularly Python, and to some extent Perl. And so we wanted to come up with a system that would be able to combine SQL and some of these scripting languages to provide a best in sort of a good hybrid experience to these kind of users. In the meantime, as we were sort of building this out, the company was growing like crazy, and we were shown on the right hand side, some of the old data I still have lying around about how fast the data was growing. We were also operating the machines and making sure that it wasn't sort of failing and loading the data and all that stuff. But we somehow managed to, build something, and we got it out as an open source project in 2010. So I've always been surprised at how much impact we have ended up having on the world at large. I think it's just a combination of being in the right place at the right time to some certain extent. I moved back to India many years back, and when I would walk around the streets, India has a lot of solutions integrators and a lot of companies, doing consulting work. And I would find every lamppost, every sort of place where you could stick a flyer in, covered with all these big data training sort of programs. And Apache Hive was everywhere, along with, of course, Hadoop and Spark and all the other things. So it had a massive impact on the ground. There was obviously a big transition in terms of proliferation of large data, storing it in Hadoop, and there was a huge need to be able to process the data in an easy, reliable manner. And the system we built essentially filled that need and became very popular. And of course, it was open source, so that helped. It was open source and free. Looking back, these are the things I think we got right. So we built a relatively complete solution. Hive was a schema catalog, plus it was a SQL engine. It had some scripting support, and it came with a few sort of data formats and a prescriptive layout sort of format, which was good enough. And all of these together allowed people to sort of just implement something right away instead of having to depend on a boatload of like 5-6 different systems. From the get-go, it was designed to work very seamlessly with Hadoop and HDFS. And so anybody with a Hadoop deployment could easily install Hive and start doing some analysis. And while Hive was slow and sometimes famously slow, I think there have been more papers written on showing systems that were 10x or 100x faster than Hive. But it was very reliable, and it just work in large part to the MapReduce implementation that came with the original Hadoop project. All of these made it very popular in a large number of settings. The second thing that I think has held up its popularity is the fact that we built a schema catalog which was decoupled from the query processing engine, and as almost a completely separate project with its own APIs and so on. And this really allowed the ecosystem to build around the schema catalog. So as time has gone on, there have been many new processing systems. Obviously, Spark, which was just mentioned, Presto, Impala, Dremio, Drill, and it just goes on and on. There's a profusion, continual profusion of new sort of distributed query processing systems. But almost all of them use the Hive schema catalog as their source of truth in terms of data sets and formats and so on. Hive made popular a pluggable storage format architecture, which we had initially named SERDES and then was called storage handlers. And that was a good choice. You know, it allowed us to plug into many different formats. It allowed innovation in terms of the data format. And that architecture, you know, was repeated in many of the other systems that came along later. And finally, I think one of the lasting contributions we made was a good choice of block columnar data storage very early on. The first version we built was called RC file, and now it has been superseded by subsequent versions called ORC file and Parquet. But again, you know, we made a relatively correct sort of architectural choice, and the block columnar format became really popular in this ecosystem and completely dominates the you know, the storage sort of format today. As a fast project that had no idea, you know, how much impact it would have in the world, and you know, I had very limited objectives, we got a lot of misses. So just thinking back, you know, I think while we tried to do some marriage between SQL and scripting languages, it was not as good as it's simply not as good as, for example, what Spark did. And that model, you know, has proved to be way more popular than what we did, and we were not really able to improve it, you know, beyond whatever we released in the first few versions. We, you know, did not really think of Hive as a server. We were sort of, or at least we did not focus as much on that part. So it had a very poor sort of a server architecture in the sense of, you know, a server that you would connect to and get things done, which would sort of know your ID, it would know your session, it would cache things for you, and so on. And so that has always been an Achilles heel of the project at large. A very simple miss, but something that, you know, probably we were not aware of the importance of when we were building this out. Third, more importantly, we built the system in the context that we were in, which was, again, unfortunately, at a company like Facebook and all the other high-tech companies in Silicon Valley. There's a lot of highly skilled engineers, you know, who can take responsibility of loading data, formatting it correctly, laying it out correctly, and so on. But that approach does not really work, you know, beyond the initial sort of early adopters. So data loading and organization is a weak spot for Hive and of the big data system at large, which depends on the Hive schema catalog and some of the methods that were initially sort of built out there. Some of the newer things I'm observing are that we did not, you know, expand the catalog to go beyond the schema metadata. And what happens is whenever you leave, there is a demand for strong demand in the system for metadata beyond the schema catalog, particularly around dependency management, lineage, and so on. And that has led to, you know, fragmentation in the field, which almost never helps. Particularly in the case of metadata, it never helps. And so there was a missed opportunity, you know, to build the Hive catalog to be a little bit more than just a schema catalog. And lastly, you know, Hive always sucked in single system performance, and even today, you know, single system performance or small query performance are very poor, and they turn off a lot of users. So that was, you know, an early miss. I don't think we saw the impact that it would have on the system at large as it sort of, you know, gained acceptance widely. Looking forward, so Ashish, myself, Namit, you know, we run a cloud-based big data analytics service. We have, you know, a lot of customers, a couple of hundred customers, all doing sort of big data processing in the cloud. So we still continue to have a lot of exposure to this field at large and what problems people are facing. And the problem sets have changed, you know, and in the obviously in the 10 years that have passed. So when we, of course, started out, you know, there was a lack of easy to use programming language interfaces, and we did some innovation there, and there was literally nothing. So we built out the basic stuff. But of course, now the problem is the inverse. You know, there is a profusion of sort of different query processing frameworks on top of large data sets. And that itself is not a problem anymore. But what has turned out to be a very interesting problem is managing cost. Of course, managing cost was always a problem. You know, we spent significant amount of time at Facebook, not writing software, but actually operating the service and actually making sure that it operates within a certain cost window. But it has become an almost overwhelming problem, I would say. because of, I would say, three factors. One is that all this innovation in terms of sort of building these frameworks with easy interfaces and so on has democratized large-scale data processing. So anybody in the company, can log into some system and fire a query that can scan terabytes or even petabytes of data. And of course, that leads to high cost. The cloud has made it worse. So we as a company, Kyobo, we are totally focused on the cloud, and we take pride in the fact that, it's very easy to sort of provision and run and sort of fire up queries, in a sort of a serverless manner. But what that does is it sort of makes the problem worse, because now you're not even constrained by hardware limits. People can just come in and sort of, spin up more and more hardware, and therefore, incur more and more cost. And finally, the nature of organizations is changing. More and more people in the company are capable of analyzing, mining data, and so the number, the base number of analysts has also increased massively and continues to increase. And with that, you get sort of sprawl, right? You get a lot of people writing similar queries, even writing similar pipelines, and potentially, a lot of wasted sort of dollars. Managing reliability of data pipelines continues to be a huge problem. So once people get beyond sort of the basics, they struggle with data quality, they struggle with dependency management, and the open source frameworks don't really do these things very well. And finally, there's a generic problem of the open source sort of the world, which is enormous complexity. If you go into any data team which operates on large-scale data sets, you'd find that they work with tens of open source projects, if not more. And there is basically dependency management hell. They're just sort of trying to make different versions of the software interoperate with each other in a correct manner, and then when you try to upgrade and change things, things break and so on. So the complexity is a huge problem. That is actually all I had. Yeah, let me just stop here, and I want to convey a very big thanks from the Hive team for recognizing our work. I'm reachable at this email, and happy to take any questions.
Right, I have
Thank you
a
very
question.
much.
Oh, is there?
Go ahead.
Can I ask a question? Right. So this is, we've used Hive for a lot of our implementation projects. And my question is, why wasn't Hive adopted at Facebook?
Hive was adopted. Sorry, I'm not sure I understand the question.
No,
So Hive was.
Okay, what I mean is Facebook still using Hive? Because you all made it open source. It was developed by Facebook, yeah.
Yeah, so Facebook was, while we were there until 2011, 12, or even 13, it was almost everything was in Hive.
Yeah.
Subsequently, there were two systems that came into place. One was Presto, and Presto got widely adopted because Hive was not good enough for ad hoc interactive queries.
Mm-hmm.
So then there was at a large company like Facebook, there's always multiple systems. So Presto started getting used for more ad hoc interactive queries. And there was also a system called Scuba, which was an in-memory system for analyzing logs. And that was very popular for operational queries. So my understanding is that even today at Facebook, there's a combination of these three systems: Hive for sort of batch pipelines and sort of, really big honking sort of reliable stuff, and Presto for ad hoc SQL, and Scuba for, in-memory sort of interactive query processing.
Okay, thank you very much. Thank you.
Thank you. Any other questions?
I have a question, actually, comment that there was controversial criticism on MapReduce is a major step backward by Stonebrick and DeWitt. So what is your thought at the moment?
Yeah, I run this company. A few years back, we built some conference rooms, and we named one of them after Stonebreaker. And we actually put his quote in one of our conference rooms. That I think I don't agree. In the sense that you climb a ladder one step at a time. We were building frameworks for large-scale data processing, and we had very little time. And so people build the first step of the ladder, and Of course, as time has gone on, people have built subsequent steps in the ladder. So nowadays, people have more complex sort of multi-stage query processing, DAGs, and so on, right? But the reality is that even if you go today and you talk to a Spark developer and you try to understand what their program does, they will often say, oh, this is the map stage and this is the reduce stage. And when we even look at competitive systems, or even we look at Presto, which is a pipeline system which doesn't have sort of anything to do with map reduce, well, okay, that's the equivalent of the map stage, and there's some shuffle happening, and that's the reduce stage, and so on. So I mean, the reality is that we are still sort of all operating in spite of all this innovation in sort of that terminology, and things have changed, but evolved sort of incrementally. And on the other side, the checkpointing sort of strategy of MapReduce has been the thing that has saved our ass. It is the thing that allowed reliability in large-scale data processing, and that was invaluable in these settings. Speculative execution, checkpointing, restartability, those were so useful. And the systems that, unfortunately, I mean, I don't want to refer to Professor Stonebreaker, but, if you look at systems like Presto, which are heavily pipelined, or BigQuery or Impala, they actually do very poorly in long-running computations because they don't have checkpointing, they don't have restartability. And another thing that's happening in the cloud is that we are working with cheaper hardware that can be restarted at any point in time. So for those of you who are familiar with AWS, they have things like spot instances, and every public cloud nowadays has equivalent of spot instances. And those architectures that were heavily checkpointed work wonderfully in computing environments where hardware can come and go. Whereas, heavily pipelined processing actually just absolutely does not work. It just sort of works for ad hoc applications, but is not able to take advantage of such hardware. So I think the reality is much more nuanced than, taking a blanket black and white position. I think, for different classes of applications, different architectures are optimal. Maybe we should use the quote in the previous talk that one size fits all is not correct, so use the right architecture for your for the right application.
Okay, thank you.
Great, thank you, Joydeep.
Thank you.
With that, let me continue the session. The closing remark that I want to say is, again, I've been serving as the chair for 2 years, and my time is over. I just would like to announce the next TCDE Awards Committee Chair, who is Natasha Alyamaki from EPFL, who will take over starting next year. And with that, we're concluding the session. Thank you very much.
Thank you very much, Johannes. And just an announcement, we had run a little late now, but I would like to invite everybody to continue with the next sessions. There is in this room the next tutorial, data science and blockchains, and in the other rooms there is the PhD symposium and the research sessions. And again, congratulations to all the people that received the awards, and we are very excited and also really appreciate all the work that went into this. Again, I'm going to stop recording now this session, and I guess people are free to kind of go to their rooms.